Okay, hi, let's get going here with section 3.3. We're going to continue our discussion about properties of functions. And today we're going to start talking about whether or not a function is even, odd, and then there is a third option, which is neither. So let's look at these definitions. A function f is even if for every number x in its domain, the number negative x is also in the domain, and f of negative x is equal to f of x. Furthermore, the point xy is on the function, and so is negative xy. Even functions are symmetric with respect to the y-axis. The next definition of function f is odd for every number x within its domain. The number negative x is also in the domain, and f of negative x is equal to negative f of x. Furthermore, the point xy is on the function, so is negative x negative y. Odd functions are symmetric with respect to the origin. So the question is, and then of course, if a function does not fit into any of these, and they could be neither. So how do we test it algebraically? Well, we use this piece in these definitions. So if we plug in negative x and we get the original function back, meaning that the function did not change, no signs changed, then that function is even. And if we plug in negative x and we get the exact opposite of that function, then the function is odd. And if neither one of those happen, then it is neither. So let's take a look at these functions and determine whether they are even or odd. So the test for even or odd is to plug in negative x. So let's plug in negative x here and we get negative x squared minus 6 is equal to x squared minus 6. So that did not change. So we can say without a doubt that f of negative x is equal to f of x. So it is even. Let's take a look at this one. We're going to go g of negative x, stuck that in. So we have negative x cubed plus 2. Well, that's equal to negative x cubed plus 2. But that's not the exact opposite. So we can see here that g of negative x is not equal to negative g of x. And this is neither even or odd, right? Because it's not equal to g of x and it's not equal to negative g of x. It changed, that power on that variable changed, and so it is neither even nor odd. Let's look at this next one here. M of negative x is equal to 5 times negative x cubed plus 2 times negative x. That's going to give us negative 5x cubed minus 2x, and that is negative of the original function. So this guy's odd for sure. And before I do the last one, let me just line out for you kind of some basic guidelines, okay? So the function's going to be even if, and this is generalized, but usually works, even if all variables are of an even power and constants are okay. So if you have a constant in the equation, that's okay. It's odd if all variables are of an odd power and there is no constant. And we can see that when we look here at G, these are odd variable. That's an odd power on the variable, but there was a constant, and the constant power won't change. But on M of X, both of those are odd powers. We have X cubed and 2 to the X to the first power. Those are odd numbers, and therefore that guy turned out to be odd. Okay, that's just a little side note there. Let's take a look at the absolute value. The absolute value doesn't fall into either one of those categories because there's no power on it. It's actually under a function. So let's take a look here. H of negative X. Well, let's see. When we plug in negative X here, well, by the definition of absolute value, it gives you the original back. Therefore, we can say without a doubt, H of negative X is equal to H of X. So this guy is even. Now, do you have to do all of that work? No. If it falls under either one of these categories, you can indicate even, odd, or neither as long as it's a polynomial. When it is another kind of function, like this is an absolute value, or if it was a radical or something like that, then you would need to apply the procedure to determine whether or not it is even or odd. Okay. Now the next concept is increasing and decreasing in constant intervals. Okay. And before I get all involved in that, I know I'm going to get distracted because I'm going to be all in it. So let me talk about today's silly quiz prompt, and it is: the carpet is complicit. Oops, wrong direction. The carpet is complicit. Okay. All right. So let's look at these definitions. And again, mathematical definitions are really, really important for you to get comfortable with seeing, be able to read, and kind of understand. They're kind of written in a way that sometimes are difficult to understand. So let's look at the first one. The first definition says a function f is increasing on an interval I for any x1, x sub 1, x sub 2, so that means any two not the same x values that are within that interval. And if x1 is greater than x2, then the function of x1 is going to be greater than x2. So that is the technical definition. We're going to get into the practical stuff. Let me just get through all the technical definitions here. Okay. A function f is decreasing on an interval I for any x sub 1, x sub 2 elements of I with x sub 1 less than x sub 2, then the function evaluated x sub 1 is always going to be less than the function evaluated at x sub 2. And then finally, a function f is constant on an interval I if for all x in I, the value of f of x is equal. In other words, when you plug in 1 for x, you get 2 for y. You plug in 7 for x, you get 2 for y. You plug in negative 19 for x, you get 2 for y, meaning every value you plug in for x, you get one consistent value for y. That would be a constant interval. Now, we always use x values, like with the domain. We always use x values when we're looking at describing what's happening on a graph. The only time we use a y value when describing what's happening on a graph is when we're asked for a range. Every other time, it is always going to be referring back to the x values, and you'll be looking from left to right to kind of read those intervals off, okay? Similar to the domain that we did in the last class, all right? So let's look at this. I have a pretty picture I drew. It's not that pretty, but it's the picture I drew, okay? Now, excuse me. This is extremely visual. It is literal and it is visual. You start from the furthest left and you move all the way through to the right. Now you can see right now that we definitely have from left to right. We're decreasing and then we increase and then we're flat. So we're constant and then we decrease again. Okay. So let's kind of break up these areas of decreasing and increasing and constant. So we can see starting right here, this graph, if we're looking from left to right, that's the key. When you're looking from left to right, it's kind of going downhill, right? And it goes downhill. My lines are going to be cruddy here, but that's okay. It goes downhill until we get to X is equal to -4. Remember, X values only. And then when we start here at -4, looking from left to right, it goes uphill. So we're increasing, okay? And then from 0 to 3, after we get there, it changes directions and it's flat. And then it goes back down. Now, this is like domains in the sense that we might have unioned groups together, unioned regions together. Okay, so let's look here. Let me go ahead and I'm going to go ahead and write the rest of my little lines that separate kind of the regions here. Okay, now it doesn't matter what order you do this in. Your homework is going to tell you what order to do it in, but because it's going to ask you, but I'm just going to do it from left to right. So we're going to have increasing, which I shorthandedly write like this. We'll have decreasing. And we'll have constant. So let's start off with the with the decreasing, because this is right here. We start decreasing when X is equal to -6. And we decrease until X is equal to -4. X values only. Okay. Now, are we decreasing again anywhere else? Yes, but I'll pick that up in a minute. Now I'm going to pick up at my -4. And what's happening from -4 until X is 0 is we're increasing. So from -4 to 0, we're increasing. And then we are from 0 to 3, constant. And then we pick up here from 3 to 6, where we're decreasing. So we're going to union our other interval of decreasing with that. And we're going to say 3 to 6. Okay. Oh, well, I wrote it all in one thing. I didn't even bother to look at my questions because I knew I had more questions. Forgot I made it in 2 things. But anyhow, here it is. Now let's answer some more questions. I think I have more questions. No, that was it. Well, I'm going to ask a couple more questions. Let's see above. See above. Okay. So let me ask this question. D, my question for D. What's the domain? So let me give you a second to write out the domain. And actually, this should be a hard bracket here because this is an endpoint with a dot. Now I know that there's points in between here, but that's a very brief turning point. So they don't get a hard bracket, but the endpoints do. Okay, do you have the domain? Yes, we start at -6 and we go to 6. Can you predict my next question? Yeah, range. This is, again, the only one that we use Y values. Okay. And the range is going to, and now remember when you do the range, you start from bottom and go up to the top. So the lowest value is -2. This is this is it. And the highest value is 4. Okay. Let's see here. I think I have one more example like this. I'm going to do something I haven't done before, which is bust out my graphing calculator. Here it is. If you have not been using an online graphing calculator, this is TI-84 Calc. It's the online one. There's the web page, right? Or there it is right there, TI-84calc.com. It works really, really good. It's just like having your handheld. And so let's take a look at this guy and let's graph it. Okay. And I just wanted to make sure everyone kind of knew how to graph things on their calculator. So this button right here, this XT theta N, this is the variable button. That's the button that you use no matter what the variable, what the independent variable is that you're using in your problem. This is the button to use, and it's always going to show an X. I mean, you can change your modes, but there's no reason for you to do any of that. There won't be a reason for you to do that until like calculus 3 if you stay with calculus. Now, I can't speak for physics and stuff, but I really, the only thing I can think of, and I took a few physics college courses, the only time I can think is when I was in Cal 3 that I actually had to do this, or maybe the very end of calculus 2. But anyway, let's go ahead and graph this. You'll be happy that you know if you don't already know. So we're going to say x to the power of 3. Then you have to use this arrow here. This was the thing that made me so mad when they changed to this nicer graphic. You have to arrow down because your cursor was stuck up there. See, stuck up there in the exponent. So you got to arrow down, and then we're going to say plus x squared minus 10x plus 8. And let's just get a graph of that. Now, I have already graphed it, of course, and I fixed the window, but let me show you how I fixed the window just in case. So let me go back to what you would see generally. You would hit this, you'd hit this thing, it'd show you the standard window, and you're like, I don't know where it turns. I can't see it all. Excuse me. Well, I noticed that it's cool down here on the bottom, right? I can see everything I need to see on the bottom. This goes on forever to infinity. I can see where the graph turns. So I went up here to the window, and this will change the scale on how many ticks up or wide it goes, okay? So I'm going to go to the window, and I'm going to change my Y maximum to something bigger than what it is, just so I can see where everything is changing over. And let's just go for like 20, which is what I tried first, and it wasn't quite enough. So sometimes you just have to play with it. Go down. And I changed it. Let's see. Let's try 25 just for the heck of it. 25 did it. Okay. So the scale here, all the way to the top, that's 25. But across here is 1, 2, 3, it's the regular scale. Okay. All right. Now that we have a picture, I like to determine where it is changing direction. And this is kind of a kind of an eyeball thing. Let me make my graph bigger now. And it looks like at -2, that might be the highest point. And I'm going to call it close enough for government work. Okay. So right there, that looks like -2. And then over here, this looks like exactly between 1 and 2. So we'll call that 3/2. Okay. So, and I don't think I can write over here on this. No, but I'm going to kind of direct with my little marker. I don't know. This doesn't really have a pointer on it. No, I don't have a pointer on this. Okay, so looks like from -infinity, because that's furthest left and nothing else is going shaking around. You've got to trust the fact that when it goes off of the graph and you've captured all of the motion, that the ends are going to the infinities. Okay, so we got -infinity all the way to -2. We're increasing. So we're increasing from, oh, that sucks. I'm going to have to go back and forth like that. Okay. So we'll just talk it through real quick. So we're increasing from -infinity to -2, and then we start increasing again from 3/2 or 1.5 to infinity. So let's write that in here. So we go -infinity to -2 union 3/2 to infinity. Now, if we go back here and look, there weren't any constants, so we can just go ahead and write none here. And then for decreasing, we'll look again here. That is going to fall between -2 and 3/2. Now, also notice that this is all going to make a chain and everything connects. Your intervals of increasing, decreasing, and constants have to encompass the entirety of the domain. Okay, and here, for this particular problem, what is the domain? Just for giggles. Let's remember what messes up the domain. The domain is all real numbers except only two things, right? Can't have a 0 in a denominator and can't have a negative square root. There's no denominator and there's no square root. So the domain here is -infinity to +infinity, and we've got to capture all of that. Okay. Okay. So let's move on. All right, more definitions. I told you this was the definition chapter if I've ever seen one. The next definition is let f be a function defined on the interval I, and let c be an element of I. And let me just take a side note and make sure that I'm not losing anyone on that kind of idea. This is the Cartesian coordinate plane, right? And whatever, we could call this interval I. So basically, when we say It's defined on an interval. It could just be any interval between negative infinity and positive infinity. Okay. All right, so let f be a function defined on interval I, and let c be an element of that interval. So that means c is in here someplace. Okay, so a function has a local maximum at c. There exists an open interval I containing C, and I guess my picture's not right because I have drawn a closed interval. So let me draw an open interval. That would be parentheses means it's open, means that there's no, you can never actually touch the ends, right? You just get infinitely close and you never get there. So an open interval in I containing C such that f of C is greater than f of x for every x in I. And f of C is called the local maximum forming the point. And so what we're kind of talking about is we're kind of talking about a graph that looks maybe like this. Okay. So right here would be considered the local. Oh, that wouldn't even be, wait, hold on. Let me take that back. We'll look at some better examples. Let me not ad lib here. Let me just get these definitions done. My bad. Okay. No, I can't. I have to explain it. Okay. So we're basically looking at something like a graph, and it could be anything, but let's just do something like this. And let's look at the interval between here and here. So we're only looking at this piece in here. This point right here would be a local max. And actually, my picture's a little bit wonky. Let me fix it. Well, I fixed it real good. Now I'm too deep in teaching this class to stop. And you guys already know I don't edit. So I'm just going to leave this in. You're just going to have to suffer with me. Can't decide how I want to show you this, and I should have thought about it before I was standing here, but this is what would happen if we were live in the classroom and I tried to show you something I hadn't actually planned out, and I'm like, wait, that isn't really right. So let me draw it one more time because I like to be persistent about it. And let's draw something like this. Because this will be a better idea for the first time you see it. And let's make our interval from here to here. And in just this piece right here, this would be the local max. And this would be the local min. So what I mean is that all the function values, so what this says here at local max, for the local max, it says that the value of this number is greater than any other number. That's what that f of c greater than f of x means. And so for the local minimum, it is the exact same definition, but it says f of c is less than or equal to all f of x for every x element of I. Just some math shorthand. I'm getting tired of writing all the extra words. Okay. So this is what these two definitions demonstrate. Okay. So let's look at a picture that is done better. Okay. So for this particular picture, we want to know at what X does G have a local max? Okay, so where it has a turning point. Usually maxes are turning points. And here we have one right here. And we can say the local max is the point 1, 2. Now your homework might ask, and I haven't assigned it yet, and I'm fixing to do that as soon as I finish recording this lecture, so it'll be assigned here in the next couple of hours. But I'm not sure if it asks you to say X is equal to 1. If that's the case, I despise that because you need to always think about points as being an X and Y. But either way, I want to point that out that your homework might ask you a little bit different. At what X does G have a local minimum? Well, here is a minimum, but this is a more minimum. If we were talking about the interval from here to here, then this, of course, would be the minimum. But if, say, we were only talking from here to here, then that would be the minimum. Okay, so it just depends on the whole grand scheme. So let's see, the local min would be what then? Yeah. X is 3, Y is 0, or X equals 3. Now let's indicate our intervals of increasing and decreasing function here. I'm going to erase all this stuff that I've written. And we're going to pretend that this is a little bit more exact than it actually is. And I like to put little lines anytime the direction changes, because that tells me those are the X values. Boom, boom, boom. Can you see it across here? So we've got negative infinity goes to this guy, then in between these two guys, then in between these two guys, and then to infinity. And that's what those turning points give us. That's what these are. Every time the graph changes directions, it's called a turning point. And a turning point is an important feature on a graph, okay? Because it indicates maxes and mins and things like that. All right, so let's get our increasing intervals. Let's see, we start increasing at, I'm going to put these numbers in, -1, 1, and 3. So we start increasing from -1 to 1, and then we pick up again and start increasing again from 3 to infinity. And then we look at the decreasing. We're decreasing from negative infinity to -1 and 1 to 3. And again, like I mentioned before, all of these intervals have to like connect so that the entire domain is covered. Let's just cover our rear ends here. What is the domain of this function? The domain, we start from the left. There's an arrowhead. An arrowhead indicates it's going from negative infinity. It's the going on forever and ever and ever in the negative direction. And an arrowhead here doesn't even matter which direction the arrowhead is headed. It's still an arrowhead indicates that it is going to forever widen and broaden out until infinity. And so this guy here is indicating we're going to positive infinity. So our domain here is negative infinity. to positive infinity if we want to look at the graph. Now, if we had the equation, we would know really quick because we would look to see, is there a square root? Is there a variable in the denominator? Okay. Now, this is a redundant part that seems silly, but there's a lot of redundancy in mathematics, in learning mathematics. So let's hit this up. Let f be a function defined on an interval I, and let c be an element of I. If there's a number u for which f of u is greater than or equal to f of x for every x element of I, then f has an absolute maximum at u. And the point u, f of u, is the absolute maximum of f on I. Additionally, same thing, but if f of u is less than f of x for every single value on I, then f has an absolute minimum at u, and the point u, f of u, is the absolute minimum of I. To be noted, there is no guarantee that there will ever be absolute extrema. You will often have local extreme there are cases where you don't have absolute extrema. Let's investigate, okay? And in those cases you deal with local extrema, or there is no extrema. And extrema is just a way to talk about the maximums and minimums. It's just a way for me to quit saying maximums and minimums. I can say extrema, and you know I mean both of those. What's happening in the extreme ends? Okay. Let's keep on going. So let's look at some graphs here, some of my lovely handy work. And what we're going to ask is we want the extrema. So I want several things when I say extrema. I want max, min. I want increasing intervals, decreasing intervals, constant intervals if there are. I'd like to also ask what the domain is and what the range is. So I'm going to ask all of these questions. That's what I want for each one of these guys. What happened there? I don't know. Okay. All right. So let's do the first one here. The absolute extrema. So the very highest point and the very lowest point. The maximum, the very highest point, is right here, and that point is 2, 1, 2, 3, 4. So my max here is 0.24. What is the min? Well, that's something we need to discuss. Is this guy the minimum value, or is this guy the minimum value? Well, the point on the left has the smaller y value, therefore it is the min. So that is going to be 0, 1. Then I want our increasing interval. We are increasing from where x is 0 till x is 2. And we are decreasing from x is 2 to x is 4. Our domain, and because these are not arrows and they are hard endpoints, our domain is from 0. It's a closed interval from 0 to 4. And our range, again, is the only thing we do with y. Start from the bottom and go up. It's the y value, so our range is 1 to 4. All right. Let's look at this next guy here. Max. Highest point, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. I could have been nice and put things like that on here, huh? So our maximum point is 5, 5. I do not know why I put it in square brackets. You don't put points in square brackets. Points go in parentheses no matter what they are, right? How about our minimum? Now you might say it's 3, 0, but notice this is a whole. And that means that that value doesn't exist, only getting infinitely closer and closer and closer to that value. And there's no way we can write that number down because that is an infinite number in itself. So there is no minimum here. Even though you can clearly see that there is a bottom here, there is no absolute minimum. All right. Okay. Let's look at our increasing intervals, and our increasing intervals start at 3 and go to 5, open parenthesis, because, yeah. And actually, I'm always a little bit, you guys let me know. I don't know on increasing and decreasing intervals, except for when there's an endpoint. No, I'm going to stick with what I know. When there's an endpoint, you got to put that, okay? Decreasing, that starts at 1 and goes to 3. The domain, smallest x to largest x, is going to be 1 to 5. And the range, smallest y to biggest y, is going to be open parenthesis 0 to 5. All right. Let's have you do this one. Yes, there will be a constant part, but you do this one. Okay, well, let's talk about it then. You should be done by now. Our max is 0 and 3. Now, our min, you should have been a little bit perplexed by the min because you see there's 2 of them. And in fact, there's an infinite number of them in between. So there is no min because there's infinite x values in between those two. So there is no absolute min. Okay, it's not one unique point. Our increasing intervals looks like 1, 2, 3, 4. That's 4. That's 2. That's 6. That's 3. And that, well, I guess that's about 3.5 there. Okay, so I'm just going to do my range real quick. We're going to go 1 to 3.5 ish. I know your homework won't take an ish, but when I'm drawing it, then sometimes we might have to throw an ish out there. The domain is from 0 to 6. We were constant between 2 and 4. We were decreasing from 0 to 2, and we were increasing from 4 to 6. And again, your homework might not, I don't know. I could be having a ghost memory, but this is what my gut's telling me to do, and I've been doing this a long time. Okay. All right, let's move on. Oh, wait, there's more. Awesome. Let's find these. So again, let's find our max, our min, increasing, decreasing. There's no constant here. In fact, there's not any decreasing, is there? No. Domain and range. Okay, so our max, there is none, right? Because this arrowhead goes to infinity this direction and goes to infinity this direction, just by that arrowhead being that arrowhead. So there is no absolute. We could say that this function had one, but we would have to identify a small interval, and then it would become local, not absolute. Absolute is applied to the entire equation. Minimum, yeah, we got that, 0, 0. Increasing from 0 to infinity. Decreasing, none. The increasing interval is the same as the domain. And the range happens to be the same as the domain as well. Okay. And then finally, this guy, we got our max, we got our min, we got our increasing, we got our decreasing, we got our domain, and we've got our range. And this is a kind of a special function. And again, I just drew the picture, but you may not be familiar with this light dotted line here. This is called a vertical asymptote. And we will study these in the beginning of pre-calculus. It's usually a topic for college algebra, but the way that we work ours here, they've moved it into pre-calculus. But either way, this is a vertical asymptote, and you don't need to know anything about it. You'll learn it in pre-calculus, but what you do need to know is it's an imaginary line that the graph will never cross. It just gets infinitely closer and closer and closer to that line. Okay? So it's a vertical asymptote that the graph will never cross. Just get infinitely closer. Okay, so now we'll go back, we'll answer these questions. What is the absolute max? Now, you might think here, but again, this has got a hole, so it is not, and we can't count anything up to that. So the next place that there is a local max is going to be right here. That would also be the absolute max because this is the entirety of this graph. It doesn't go any further beyond the left of x equaling 1. And because of the nature of a vertical asymptote and the direction that this graph is going already, it will not be able to turn around and come back up. It can't cross that dotted line, and it's just getting super duper close to that dotted line. Okay, so our local max is going to be 1, 2, 3, and whatever the heck that's supposed to be. 3 and 3. No absolute. We have a local min of 2, 2. No absolute because this graph keeps on going, right? It's talking about this whole graph, so no absolute. We are increasing from 2 to 3. We are decreasing from 1 to 2 and 3 to 1, 2, 3, 4. The graph will not go any further than 4. Even though it's an arrowhead, there's an asymptote there. That's why I'm pointing all of these little special details out. Okay. Do I think you're going to have a problem like this? I don't really, but I really wanted to be explicit in showing you where you could have local mins and local maxes, but not have the absolute mins and the absolute maxes. And this is like a really good example of that. Okay. And then our domain here is going to be X is 1 to 4 open because you never get to 4. And our range is going to be looking from the bottom, negative infinity, last Y value, 4. Okay. Yay. All right. Okay, I know this has been a lot of concepts. We're on the last concept this week. Last concept for the week. There'll be plenty of concepts next week, but this is the last one here. Let's get going. Suppose the domain of f of x is an interval of I. If a and b are elements of I and a is not equal to b, then the average rate of change of f from a to b is defined by this definition. Average rate of change is equal to the change in y. That's what that delta means. That means it's the change in y over the change in x. Okay. And this is how we'll define it. F of b minus f of a over b minus a. You don't really need this stuff. That's just me showing you what I mean. A has to be smaller than b and a is not equal to b. Okay. Now, what are the steps to find the average rate of change? Well, first we find f of b, then we find f of a, then we plug it into the formula. Okay. And this is the point A, B. Okay. So first we find f of b. So we're going to say f for this case, we're going to say f of 4 is equal to 2 times 4 squared minus 3, which is 2 times 16 minus 3. 2 times 16 is 32, minus 3 is 29. If we were in the classroom, I'd tell you to double check me, but I can't tell you that. I'm really crappy at arithmetic, okay? And now we find f of a. That's f of negative 1. That is 2 times negative 1 squared minus 3. It's going to give us 2 times 1 minus 3. It's going to give us negative 1. And now we're going to plug all this into the formula. And the formula is f of b minus f of a over b minus a. So our f of b is 29 minus, that's the minus from the formula, f of a, which is negative 1, all over b, which is 4, minus from the formula, negative 1. Oops, it didn't change colors. Okay, so this is going to give us 30, because minus a minus is a plus, over 5, it equals 6. So the average rate of change between negative 1 and 4 equals 6. Okay, it's really just a plug it in, chug it out kind of situation. And this isn't really a point. Let me point this out. This is the endpoints of the interval. Okay. All righty. Let's take a look here then. One last, I can't wait for it to be over. One last and final definition here. The average rate of change should have felt a little bit familiar. If it didn't feel familiar, then that's okay. It's been a long class, but it is actually the slope between 2 points, right? Y minus y1, the y part minus the y part over the x part minus the x part. Exact same thing. Now, the line between 2 points on a function like this is called the secant line. And let me just draw you a little quickie picture. This isn't going to be like my last quickie picture. So say we have this point here and this point here. That would be the secant line. Okay, so let's do this last one. It says, given w of x is equal to 3x squared minus 3x plus 3 on the interval negative 2 to 1, remember this is A to B, find the average rate of change. Average rate of change is f of b minus f of a over b minus a. So we're going to have to find our f of 1 first. That's going to be 3 times 1 squared minus 3 times 1 plus 3. That's 3 minus 3 plus 3. That's just 3. And we'll find our f of negative 2. That's going to be 3 times negative 2 squared minus 3 times negative 2 plus 3. So let's make sure we're good here. The f of b, f of a. Order matters here, okay? So this is 3 times 4 is 12 plus 6 is 18, 19, 20, 21. So let's plug it into our average rate of change. F of B minus F of A over B minus A. So 3 minus 21 is negative 18 over 1 plus 2 is 3. That gives us negative 6. And so what are the points that we are dealing with? Because now it asks us to find the equation of the secant line, including these 2 points. Well, we just found those 2 points when it's negative 2. Oops, sorry about that. We have 21. And when it is 1, we have 3. These are our 2 points from our secant line. And now we want to use point slope formula. Okay, so now we're going to use our point slope formula. We know what our slope is because this is also the slope of the secant line. So we know also this M is equal to negative 6. Now, remember, we did this a while ago, so you might not remember, but it doesn't matter which point we choose. So I'm just going to choose this point here because I don't want to deal with 21. I want to deal with smaller numbers. So here we go. Y minus 3 equals negative 6 times x minus 1. And then let's clean it up and put it in the form that the slope-intercept form. So y is equal to negative 6x plus 3. And this is our equation of the secant line. Between these 2 points. Now note, if I chose 2 other endpoints on this graph, I would have a completely different thing and the line would be completely different. And you could see that here, right? Like if I chose, say, this point and this point, that line would be different. So it's specifically the secant line between negative 221 and 1, 3 on this particular equation. Okay, we did it. Hooray! Y'all have a good week.